welcome back to another episode of Mastering Diagnostics with yours truly, Brandon Steckler, technical editor of Motor Age magazine. You know, what makes drivability technicians great technicians, it's not so much all the experience they have or how fast they are or what they know about the car they're working on. It's all that and then some. It's about being able to leverage the tools that they do have to their greatest potential to build a diagnostic game plan. And this holds true for all systems on all cars. But one where this rings true the most for me is the variable valve timing system. And here's why. With factors such as hydraulics, induction, duty cycle, and every other challenge that every other circuit on the car faces, resistance and such, it takes a multi-faceted, powerful scan tool and robust service information to get you the information you need so we spend our time diagnosing efficiently. So to do that means to not approach vehicles like it's a hobby for us, but approach vehicles and solving challenges efficiently and accurately. Because we don't do this as a hobby. You and I, we do this as a living. And like it or not, every one of those individual service bays are a business within a business. And if those individual businesses aren't profitable in the long run, we're not going to make money. So if I can use a tool multifacetedly, being able to leverage this tool from many different angles to give me information so I can make diagnostic decisions, that's going to save me a heck of a lot of time and wasted energy in the long run. And what am I trying to do? I am trying to establish what is right with the vehicle, with that system on the vehicle. Meaning, I used to approach vehicles trying to find out what's wrong. That makes sense, right? But now I find it more efficient to find out what's right on the vehicle up front. This way, when I do commit to testing an individual component of a system, when I roll up my sleeves and actually get dirty, I'm not testing every single thing under the hood. True, I could take that approach and probably find the problem, the fault within the system, but might take several hours, several days, heck, maybe even several weeks. Wouldn't it be better to just focus our energy testing only a handful of components or hopefully even an individual component to find a problem? That's what today's episode is all about. It would be great to possess a scan tool that offers me Wi-Fi connectivity to the internet. This way I can access service information about the car I'm working on right then and there. Being able to scan for DTCs to see where faults lie. Research them, research wiring diagrams, develop a diagnostic game plan. Leverage the power of that same scan tool to perform system tests through bidirectional control, and then individual component tests through bidirectional control to see what is working and what is not working. And when I find the problem, commit to hands-on testing under the hood, heck, sometimes with the same scan tool. And I have to thank Bosch Diagnostics again for letting me use their ADS 625X scan tool, because this scan tool does everything I just described right from the driver's seat. It's phenomenal. So I'm going to be working on a 2009 Acura RDX with a dual overhead cam 2.3 liter engine. And although this vehicle does not currently have a fault, we're going to approach it like we do have a fault. I want to show you technicians at home how I approach vehicle drivability faults efficiently so I can solve the problems accurately. And believe it or not, when you learn to do that, it really makes the job easy. Why? Because you have a diagnostic game plan you're going to carry out. So step one, let's head out to the vehicle and scan for DTCs.
Well, we've made our way out to the vehicle, and again, this vehicle's not faulted, so we're going to pretend like we scanned for DTCs. And I purposely chose to follow a diagnostic path troubleshooting DTC P0011, which is basically as generic as a fault you can get for the variable valve timing control system. Meaning, reading the code alone is not going to get us anywhere. There's no subtle hints saying things like circuit fault or VVT performance issue or anything like that, having trouble targeting a camshaft where we want it to go. But none of those clues exist.
So as you can see, we've scanned for DTCs. And of course, as I said, since this vehicle is not faulted, there's not a problem. But let's assume for a moment we had an issue with the variable valve timing system. Honda Acura calls it VCT, or variable cam timing. What is the purpose of variable camshaft timing? The idea is to be able to move the camshafts in order to change the breathing characteristics of the engine. In a conventional engine, before VVT or variable cam timing existed, we had fixed camshafts, meaning the grind of the cam lobes was once and done, and that's what you have to work with. Camshaft grinds can be designed to accommodate different engine characteristics. We might have engines that idle nice and smooth and perform very efficiently, but don't produce a lot of power output. For instance, an engine you might find under the hood of a small displacement hybrid vehicle, like a Toyota Prius. But then again, we've got engines that are very high output, very high torque and horsepower output that have a more aggressive camshaft grind. So as always, I want to keep this as simple as possible. In your mind, I just want you to imagine being a teenager again and mowing the lawn, with an older push mower. And think, once you got that mower started, if you were too aggressive with the throttle, what tended to happen? If you recall, if you move that throttle too aggressively from the turtle position to the rabbit position, the engine would take a tremendous gulp of air and then fall on its face. In other words, acceleration wasn't good. Well, the camshaft grind on that simple engine did not support rapid acceleration. It was designed to do one thing: cut grass. I'll give you another example on the flip side of that spectrum. Picture a top fuel alcohol dragster sitting there at the racetrack at the tree waiting for the red light to turn green. How does that engine idle? Pretty terribly. Why? Because aggressive camshaft grind. So it doesn't idle very well, but what happens when you push the accelerator pedal to the floor? That thing takes off at lightning fast speed. Very rapid acceleration. Heck, hundreds of miles per hour in just several seconds. Again, that all goes to the engine design, the camshaft grind. So I just want to flip over to a drawing I created. Pardon a rough sketch. I'm no artist. But this is my rendition of a picture of a piston oscillating up and down as it normally does during an engine cycle. And in blue, we have airflow, fresh air and fuel coming through the intake port from an open intake valve. And in red, we have exhaust gases, spent inert exhaust gases, leaving the exhaust port through the open exhaust valve. Now, I'm going to explain this same picture from two different aspects. So bear with me. Through the first aspect, as the piston is displacing the spent exhaust gases out the open exhaust valve as the piston moves up on the exhaust stroke, simultaneously with the intake valve being open through what we call valve overlap, we can scavenge the cylinder. Now here's what I mean by cylinder scavenging. If you were to watch my hands and picture me being spent inert exhaust gas leaving the cylinder, I can do this because the exhaust gases have inertia. That entire column of air leaving the cylinder has inertia, and it's going to create a siphon effect and draw fresh air and fuel into the cylinder, just like you see here. So the purpose of doing that is to fill the cylinder more efficiently. We call that cylinder scavenging. And here's the second angle I want to approach from. As the piston goes down on its induction stroke to draw fresh air and fuel into the cylinder, by leaving the exhaust valve open for a length of time, we allow for valve overlap to occur. And this creates an EGR effect because now we are sampling spent exhaust gases from the exhaust stream along with fresh air and fuel from the intake stream. Why do we do that? Well, ask yourselves, why did we get rid of EGR valves? It's because we can accomplish this EGR effect through valve overlap. If we fill the cylinder partially with inert exhaust gases that do nothing, they don't react, there's no chemical reaction taking place there. In essence, we take that cylinder and effectively make it smaller. By making it smaller, we also make the intensity of the upcoming combustion events smaller, which reduces temperatures within the cylinder and also consequently reduces the production of harmful oxides of nitrogen. So I want to move on to my next point, how we accomplish valve overlap. What we see here is my rendition of what I refer to as minimized valve overlap. So in red, we have the exhaust valve opening, its lift, its duration of time it's open, and then the exhaust valve closing point. In blue, we have the intake valve opening, its lift, the duration it's open for, and its closing point. This area I have highlighted in green here represents valve overlap. And as you can see, it's very small. So if we go back to this photo here and valve overlap, if it's reduced, our induction stroke inhales fresh air and fuel and very little exhaust gas. What does that do for us? It stabilizes combustion, meaning making the engine run smooth, and allows us to lower idle speeds. So an engine that needed to run at approximately 700 RPMs to maintain a smooth, desirable idle, we can now take it down to maybe 450 RPMs, and it will still run smooth. But what does that do for acceleration? With the reduced valve overlap, the scavenging effect doesn't take place as well. And as a result, we don't efficiently fill that cylinder with air and fuel, and we don't get the acceleration we desire. So this is where a more aggressive valve overlap duration comes into play. By maximizing valve overlap, as you can see, this green area has gotten bigger. We are ingesting not only fresh air and fuel, but more exhaust gases. And by maximizing this valve overlap, we've increased this scavenging effect, filling the cylinder with more fresh air and fuel. So that's valve overlap in a nutshell. And virtually every engine out there that leverages variable cam timing does so in a similar fashion. But there's a million ways to skin a cat, and there's multiple ways to accomplish this same goal on different engine platforms. So we have to do our diligence and do some research. So again, leveraging a multifaceted scan tool with all of its capabilities like that of the Bosch ADS 625X, I can access repair information right from the driver's seat of the vehicle I'm working on. So let's visit service information and learn about how this system accomplishes the goal of variable valve timing. As you can see here, this hydraulic routing demonstrated in red shows the path of oil flow from the sump in the oil pan up to the variable camshaft timing actuator located on the intake camshaft in this vehicle's configuration. Pressurized oil leaves the oil pump as it's drawn in from the oil pan. Its output from the oil pump is then sending the pressurized oil, the hydraulic fluid, through the block and makes its way up to the cylinder head. But before it does that, it passes through a screen that's mounted in line against the block just adjacent to the intake manifold here. So fluid enters the screen, it's filtered, and re-enters the block before it passes through the head gasket and into the cylinder head. And at the cylinder head, oil pressure is modulated. It's controlled via this solenoid, which we're going to talk about in a little bit. And the pressurized oil is directed through the hydraulic circuitry of the camshaft carriers and bearing caps into the camshaft itself through some hollow hydraulic passages where the oil is directed to one of two sides of this variable camshaft timing actuator. So again, I'm sure many of you are quite confident in your ability and your knowledge of how these systems function. But there's many of you out there that aren't. They're still new to this and they want to learn a solid diagnostic approach. So my goal is to take this step by step, how I would approach any problem, especially with a vehicle, a component, or a system I am not familiar with. So let's talk more about that solenoid for a moment. Looking at this solenoid, taking into account what I just described to you through the hydraulic circuitry, pressurized hydraulic fluid is routed to this port that you see right here. And the job of the engine control module, the powertrain control module in this configuration, is to control this solenoid to deliver fluid in one of two passages. I have this drawn to show pressurized fluid entering the advanced chamber. And as it enters the advanced chamber, the retard chamber of this hydraulic actuator is emptied or dumped through this vent port back to the sump. So if there's pressure being dropped on this side and applied on this side, it's going to cause a pressure differential, and the internal rotating member, rotor if you will, is going to rotate in reference to this stator, the outboard side of the component that is tanged mechanically to the timing chain. And on the flip side, if I wanted to bring this in the other direction, I would control the solenoid in a fashion to apply pressure on this purple circuit and relieve pressure on this brown circuit, causing this component to rotate in the opposite direction, bringing the camshaft back to its home position. So now that we have an idea of the goal of this system and what I like to call the players in the game, what components are involved in accomplishing this goal, let's talk about something that many technicians cringe when they hear this word: physics. That's right. We are scientists, my friend. Like it or not, you may not have signed up to be a scientist, but we are scientists. We take our level of knowledge and understanding and create hypotheses, estimated guesses on how components work within systems to accomplish a goal. And then we perform tests to see if these components within these systems are functioning properly. But if we have an idea of the physics involved, we can accomplish this goal a lot more simply. Why? Because physics are proven and they can't be changed. And since they can't be changed and it's something we can rely on time and time again, I say don't shy away from physics. Don't shy away from being a scientist. Embrace them and leverage them to your advantage. So the first one I want to mention is Ohm's law. Ohm's law, written out here, says it takes 1 volt to push 1 amp through 1 ohm of resistance. Let's simplify that for everybody because there's no use trying to memorize verbiage that's not going to stick in your head. I want it to be easy and applicable. So here's how I see Ohm's law. Ohm's law is the relationship between voltage, which is electrical pressure, current flow, which is the movement of electrons through a circuit, and resistance, the opposition to that current flow. Now, although this isn't technically accurate, we could think of it like water flowing through a pipe. Water pressure represents voltage. The movement of water represents current flow, and a restriction in a pipe represents resistance. The second law I want to mention is Lenz's law. Lenz's law states if any induced current flows, its direction is always such that it will oppose the change which produced it. That's going to make better sense when I get a picture of a waveform up on the screen. So we're going to revisit that in a little bit. Next, I want to mention Faraday's law. Faraday's law says that any change in the magnetic environment of a coil of wire will cause a voltage to be induced in that coil. As I mentioned at the beginning of the video, we are dealing with hydraulics and we are dealing with induction. And induction basically describes what happens when we flow electrical current through a wire. We induce or create a magnetic field. And we're going to capitalize on that magnetic field to create physical movement or shuttling. So I want you to take a look at this picture here. This is a variable camshaft timing oil control valve, a cutaway, if you will, a generic cutaway. And what we have on this side is a spool valve. That job of the spool valve is to direct pressurized hydraulic fluid, in this case, engine oil. And we control that spool valve through induction, through electrical current creating a magnetic field. Now, as you can see, the spool valve is in its rested position at the moment, resting against a spring. Now, when I energize this solenoid, I flow electrical current through the windings. A magnetic field builds around the windings, and the magnetic field creates physical shuttling of this spool valve. This spool valve will move to the left and collapse this spring. So if I have pressurized hydraulic fluid coming from the sump in the oil pan and being directed through my hydraulic circuitry up to this port here, if this valve is in the furthest left position, this advanced chamber is going to be exposed to this pressurized hydraulic circuit. And at the same time, this retard chamber is going to be exposed to this drain port. So pressurized fluid is going to enter one side and be vented on the other. And this, of course, is going to cause mechanical or physical movement in that VVT actuator. It's going to cause, in this configuration, the intake camshaft to advance. Now, if I were to turn off this solenoid and electrical current ceased to flow, the magnetic field would dissipate. And at that time, spring pressure would push this spool valve back to the rested position. And in the rested position, pressurized oil is no longer directed to the advance port, but it would be directed to the retard port. And at the same time, the advance port would be referencing this drain port here. So physical shuttling would occur with that camshaft, and it would go in the opposite direction. In this case, it would take the intake camshaft away from the advanced position and put it back in the rested or home position. So I have a problem with that. Do you know what that problem is? What I just described is energizing the solenoid or de-energizing the solenoid in a digital state, either on or off, meaning fully on or fully off. That's right, if I energize the solenoid in that fashion, the intake camshaft is going to advance to its fully advanced position. And going back to service information, you would learn that that's approximately 30 crankshaft degrees advanced. At the same time, turning off the solenoid would return it back to its home position, 30 degrees more retarded than when it was advanced. And as you can see, the problem is we need to be able to place that camshaft anywhere between the home position and 30 degrees advanced from that home position. Not only that, we have to hold it in that place when desired. So how can we go about doing that? That is accomplished through control. And the control we're talking about is duty cycle. Now, as you can see here, I've got 3 different examples of duty cycle control. This is referencing a high side driven circuit. By high side driven circuit, I mean one that has a fixed ground, and we control the circuit by turning voltage on and off. In this 25% duty cycle, the definition of a cycle is when a waveform, in this case, repeats itself. So if we go from this point here, where the voltage switches on, to this point here where the voltage switches on again, that is one complete cycle. And if you were to measure from here to here and take a measurement of how much on time is compared to off time, there is 25% on time and 75% off time. So we refer to this high side driven circuit as a 25% duty cycle. Here is a 75% duty cycle. Again, where the voltage switch is high, to the voltage switch is high, which is one complete cycle. 75% of it is spent energized, meaning 25% is spent de-energized. And a nice happy medium would be a 50% duty cycle. One full cycle from here to here, it spends half the time high or energized and half the time low or de-energized. What is the purpose of that duty cycle, or what we know as pulse width modulation? We can alter the width of the on time to control that solenoid. And we turn that solenoid on and off at the suggested pulse width very rapidly. We maintain very good, strong control of that oil control valve's position. If we go back to that solenoid picture, let's revisit it and see how duty cycle is going to affect the operation of the solenoid. Again, fully energizing the solenoid, 100% duty cycle on, is going to shuttle it this way and cause the VVT actuator to fully advance. De-energizing the circuit completely is going to cause the spring to push this spool valve to the right and is going to cause the VVT actuator to fully retard. But we need to control where we place it. So what we're going to do is we're going to change the duty cycle from something lower to something higher progressively. And what that's going to do is create fine control of how we shuttle this spool valve. It's not going to shift to the right or shift all the way to the left. We're going to move it progressively. When we do move it progressively, we are going to allow that VVT actuator to advance to where we desire it. And when it gets to where we need it, we can pause it. How are we going to do that? We are going to take the VVT oil control valve duty cycle and back it down to a point where the magnetic field strength, creating physical shuttling to the left, matches this opposition of spring pressure pushing to the right. And when we find that happy medium, we maintain that duty cycle to lock that solenoid's spool valve in its place. And that's how the picture is drawn right here. So when magnetic field strength matches spring pressure, the spool valve is held steady, which hydraulically locks the circuit and mechanically locks the VVT actuator in the desired setting. Pretty cool, huh? So how did I learn that? Am I a very smart technician? Am I a genius? No, not at all. I'm no smarter than any of you. I may have some experience in drivability, perhaps a bit more than some of you, but I learn from reading. I visited service information. Don't believe me? Take a look at this picture. Variable valve timing control system controls the timing of the intake camshaft. It uses hydraulic pressure to operate the variable timing control actuator. So valve timing is optimized depending on driving conditions. The PCM monitors phase control command and the actual timing of the camshaft by using camshaft position sensor. If the phase difference between them is excessive for a period of time, a malfunction is set and a DTC is stored. So now we have an idea of what goes wrong when we get a DTC stored, and we are going to pursue that fault. So through some more reading, we can determine what the threshold is, meaning at what point was the PCM unhappy and set a DTC. It tells us how that DTC was set and how we should be analyzing the system to get the fault to flush itself to the surface. The timing difference between the command versus the actual time of the camshaft is 20 degrees or more for at least 15 seconds. So that should give us adequate time to see the fault revealed. So what we're going to do now is head out to the vehicle. We now have an idea of what to expect, and we are simply going to drive the vehicle and see if the fault is exhibited. Depending on how the vehicle behaves is how we are going to pursue the fault further. It's time to head out to the vehicle and acquire the data that allows us to see the story being told. We want to monitor PIDs in a graphical format that will allow us to see what I call action-reaction comparative measure. We're going to be looking at multiple PIDs in a graphical format because the PIDs allow us, in graph format, allow us to see how they interact with one another. And the fact that it's graph provides a history, so we don't have to stare at the screen while we're driving. What I want to see are the actual versus desired position of the camshaft solely, because that's going to serve as a go, no-go, meaning is a problem present or is a problem not present. If I drive the vehicle looking at those PIDs and my actual camshaft position in degrees matches my desired camshaft position, it proves the entire system is working. It has to. It has to hydraulically, it has to electrically, and it has to mechanically for those lines to overlap one another. It's a tremendously powerful technique, so we're going to do that first and foremost. So let's head out to the car now.
Again, I want to implement our Bosch ADS 625X, and this wireless scan tool offers us tremendous amount of capability right in the palms of our hands. And again, being wireless, I'm not tethered to the vehicle, so I can walk around and be out under the hood if and when that time comes. But right now, let's get set up for a road test so we can view the data pertinent to the VVT system's functionality. We want to graph the data out so we can see reaction comparative measure and view this in history over time so we don't have to watch while we're driving the vehicle. So we're going to go in to Diagnostics and we'll choose a recent vehicle, and we're going to go into data stream for our engine, and we're going to customize our PID list to speed up the refresh rate of the scan tool and also just limit the data we want to view. Makes it a lot easier to make diagnostic decisions when you're not overloaded with data. So we're going to go with camshaft position control, VTC status, which will let us know if it's in that phase of operation or not. Oil pressure switch, hopefully that is pressure data and not just a digital signal, but we'll see. Camshaft command, VTC duty cycle. And what we are going to do is graph out this data. So I'm going to get rid of oil pressure switch because it's simply on and off. And we will expand these. And we will to line graph format. So we're going to go on our road test now and capture this data. So the engine is running. We're in gear right now, and I've got my foot depressing the brake pedal. Again, there's nothing wrong with this vehicle, so I'm not going to go on a road test because we're not going to see a fault. So I'm just going to simulate driving on the road conditions by gently power braking and changing RPM, and you will see as we ask for camshaft phasing, our VTC status will change from off to on. When that occurs, our camshaft position control, our desired camshaft position will change, and since the PCM desires the camshaft to move, the duty cycle command to the solenoid will increase. And because the engine RPM has increased and oil pressure has increased, this duty cycle command will only go elevated for a short period of time to get the camshaft to move. So watch what happens now. First, I'm going to slowly roll into the throttle. And since I'm power braking, it's taking 40% duty cycle at approximately 1,000 RPMs in gear to maintain the 14 degrees we're asking for. Now watch what happens when I step into the throttle. You can see immediate changes in request, immediate change in output, and an immediate change in actual camshaft position. Camshaft desired and actual match, and this is what we want.
So, of course, this vehicle does not have a fault within the variable camshaft timing system. However, we can still approach this data and learn from it. By looking at actual and desired camshaft positions, we can determine if the system's functioning properly, and obviously it has. But the duty cycle command to the solenoids helps determine how hard the system is working to get there. So there are two factors that determine if a camshaft moves and how well or how efficiently it moves. One of which is oil pressure, coming from engine RPM and pump output or pump displacement, and the other is duty cycle control of that solenoid. The more aggressively we duty cycle that solenoid, the more command we are giving it to allow more oil, pressurized hydraulic oil, flow through that solenoid, right? Like an acceleration. The less duty cycle, the less aggressive we have to be. So to create physical movement of that camshaft, it takes oil pressure and duty cycle. Being able to reflect on the duty cycle being delivered at the time helps determine how hard the system is working. And although this is a single bank inline four-cylinder engine, this technique also works great, especially on V engines, because we can compare one bank to the other. So if we had a common problem that affected both banks, it would help us determine where we begin our testing. However, if we have a fault that's related to one bank only, we can use the other bank to determine what duty cycle should be. So although this configuration is an inline four-cylinder engine, if this was a V engine, applying these techniques works great for them as well, especially when we have a single bank problem, because I can compare oil control valve duty cycle data from one bank to the next, a good one compared to the suspect bank. And it helps infer the type of fault we are dealing with. So again, I mentioned that there's nothing faulted with this vehicle, but pretend for a moment the data that we just reflected upon revealed a potential fault. What now? Basically, what we know at this point in time is a fault is present within the system, but where do we go from here? Do you really want to roll up your sleeves, open the hood, and start disassembling the engine hoping to find a fault? I certainly don't. For one, once we're in there, there's nothing we can do because the engine's disabled. And two, if we take it apart and we don't see anything with our eyes, now what? Now we've got to go back together and start over. So this is where the power of a robust scan tool with multi-faceted functionality comes into place, just like this Bosch ADS 625X. Through the power of bidirectional control, we can manipulate the entire system. And here's what I mean by that. If I enter the scan tool through bidirectional control and I manipulate the entire system as a whole, not only am I factoring in functionality and control of the components that make up the variable valve timing system, but also the computer software logic, meaning can the computer make appropriate decisions? So the idea behind this test is to request that the computer move the variable camshaft timing actuator, therefore the intake camshaft, a certain amount of degrees and then hold it in that spot. And then move the camshaft more and then hold it in that spot, meaning find a target, move it there, and maintain that targeted area. And do it a third time. We are going to take bidirectional control to manipulate the system through the computer's own logic to find three separate targets and see if we can acquire those targets accurately and efficiently within a very tight window. That would tell us if the system is functioning properly. Now, assuming we road tested this vehicle and a fault was present in the data PIDs that we saw, logically speaking, it would be anticipated that this system test we are going to go out and perform right now would fail. And that would take us closer to finding the fault by telling us which direction to head for our next test. So again, let's go back out to the vehicle and conduct this bidirectional control variable camshaft timing system test.
So let's assume for a moment after that mock-up road test, the data displayed a fault. Let's pretend my ECU gave the command for VTC to function. So our status would change from off to on. Our desired camshaft position would be 30 degrees advanced, right? In aggressive overlap period for scavenging and rapid acceleration. So we request 30 degrees of advance. Instead, we got let's say 17 degrees. And if I were to look down and see my duty cycle elevated much higher than 40%, let's say closer to 70 or 75, much like fuel trim being a corrective factor, the increased duty cycle would indicate the PCM is trying to work the solenoid harder to get more pressurized oil up to the phaser because it is lagging and it is not positioned where we desire it to be. Let's pretend that happened. What are some potential faults? Could I have a solenoid with high resistance or a voltage drop somewhere in the circuit controlling the solenoid? Yes, that would cause a decrease in available pressurized oil to the phaser. Could I have a lack of oil supply, meaning maybe the maintenance routine was neglected and the oil change interval is severely overdue and we have burned or consumed some oil and there's not enough to support VTC operation? Absolutely. Let's pretend this is a high mileage engine, several 100,000 miles, and there is some camshaft bearing wear, and the available pressurized oil has bled off across that bearing clearance. That's certainly a possibility as well. What about restrictions due to carbon in the oil hydraulic circuitry? That's going to cause a pressure drop, and subsequently, available pressurized oil is not what it should be. That would certainly cause the system to lag. What about a stuck solenoid? Right? Carbon gets in a solenoid and prevents it from shuttling the way it's supposed to. All of these are valid possibilities, and I've experienced virtually every single one of them in VTC system faults. So the point is, where do we go from here? Do we go under the hood and start tearing things apart? I urge you not to, because that's a lot of time and money and energy invested, and if we get it apart and don't see the fault, we have to put it back together before we can approach the problem for a second attempt. So now we're going to leverage system functionality through bidirectional control with the Bosch ADS 625X, and we're going to operate, manipulate the system as a whole. So let's do that now. So now we're going to go to special tests, and the special tests allow for some bidirectional control. We can manipulate this VTC system. So this is the list of all available tests. So we're going to go under Other Tests, and I'm going to scroll down till I find Intake VTC System Test. Now the scan tool will automatically issue you directions on how to carry out the test and prompt you to do things like start the test. So it says this test activates the variable camshaft timing control system in 3 stages and monitors each position based on input voltage from the cam sensor. The purpose of this test is to identify if a VTC system failure is present. And it offers a note: there can be a difference between actual and target angle of 3 to 5 degrees. So this gives up some anticipation on what to expect when we carry out this test. So I'm going to press continue. It tells me to clear DTCs before the test. Engine must not be running. And now it's getting ready to start the test. So I'm going to start the test, and it's going to tell me, start the engine, and follow the warm-up conditions. And I am to keep the engine between 2,500 and 3,000 RPMs for the test to be carried out. It says wait 10 seconds and slowly increase the speed between 2,500 and 3,500 after test completes. Hold the RPM at high speed for 10 seconds after test completes. Press continue when the range has been met. So I'm elevating engine RPM to about 2,500, and I'm going to press continue. Desired position is 20 degrees, actual is 20 degrees. 10 degrees and 10 degrees. So our test has passed. With the Bosch ADS 625X, we're able to manipulate the system in its entirety, including the logic and control from the PCM. We basically gave it a command to run its own test, and all we did was elevate the RPM to ensure we had sufficient oil pressure to drive the hydraulic circuitry. within the VTC system. So the results of our test, of course, were a pass and there's nothing wrong. But again, we're trying to simulate how we would approach a true VVT fault.
So that worked out really well. And again, nothing wrong with this vehicle, so I didn't expect this test to fail. But it was neat to see that right from the driver's seat, we can push a button and request that the computer carry out this full system test, incorporating its own logic and its ability to reflect on the camshaft position sensors for feedback to determine, did the camshaft move where we wanted it? You got to think of it from that entire perspective, how much is incorporated into this easy to perform system test right from the driver's seat without ever even opening the hood. The test showed us that we had very, very fine control of placing the camshaft where we desired. Not once, not twice, but 3 different times in 3 different locations, proving the entire system, including the computer, the camshaft position sensor feedback system, the VTC actuator, the hydraulic circuitry, and the control of that circuitry. Everything functioned great. But for a moment, let's pretend that it didn't function great and that test failed. What then? Well, we can take bidirectional control a step further through individual component testing, meaning I can command a component to function while conducting testing under the hood on the circuitry involved. And this is where pinpointed testing comes into play. But I want you to think about it like this. We didn't just arbitrarily choose to start pinpoint testing components within this system. We are using the easy-to-perform system tests, leveraging the full capability of this robust ADS 625X from Bosch to provide stepping stones for us that led us to pinpointed testing. So again, we're going to leverage bidirectional control through individual component tests. We're going to push a button to tell the computer to command the solenoid on. And while that is occurring, we can perform our testing under the hood to determine what is happening and what is not happening, meaning why is this system failing? But for that, we have to refer back to service information so we can continue building our game plan. We have to see how this system is electrically configured. So with that, let's visit a wiring diagram. As you can see here, this high side driven circuit is as such because this VTC oil control valve solenoid is provided a ground path at all times, which means we control the solenoid on the high side through a driver in the PCM, a high side driver. The PCM is going to output that square wave we discussed earlier, and that is how we control the system. So after visiting that wiring diagram, we have anticipation of how the system is going to work, which means we now know how we are going to test it. If you refer to this diagram here, I've implemented a lab scope. And what I've done is I've taken a single channel in red and placed it at the oil control valve solenoid to monitor apply voltage, control voltage to the solenoid. I've also taken a black lead and placed it here on the ground side of this VTC oil control solenoid to make sure our ground path is not interrupted. And the third channel in green, I have an amp probe placed on the circuit, anywhere in the circuit that's convenient because this is a series circuit and current flow is the same anywhere in a series circuit. The amp probe is going to show us current flow, which in essence is going to show us the work being performed. So let's head back out to the vehicle, carry out this bidirectional control of the variable camshaft timing oil control valve solenoid. And at the same time, we're going to monitor circuit activity to see or find where the breakdown in the system would be occurring. Again, this isn't a broken car, so we're not going to see a problem, but I'm going to show you the areas to look at in the waveforms we acquire to tell us if the vehicle is not working properly and the reason why.
We have to pursue the individual components relating to the VVT system. First and foremost, with electrical testing of the circuitry related to the oil control valve, because this is the heart of the system. So through bidirectional control, again with the ADS 625X from Bosch, we can manipulate the components individually. And by carrying out the special function of solenoid valve activations through mode A to the scan tool, Now we can manipulate the components individually, in this case, the VTC control actuator solenoid, while we monitor circuit activity live with a lab scope. So we go back into all special tests, into engine, and instead of intake VTC test, we'll go into individual solenoid valve activation. So let's go back inside to the computer, sit down at the desk with a warm cup of coffee, and analyze the data captured.
So let's reveal what the waveform is trying to show us. On this capture coming up, I've drawn this by hand, a view of a lab scope. And this lab scope capture shows us 3 different areas of concern. Regarding the circuit providing current flow to the variable camshaft timing oil control valve solenoid, we've got our ground reference that's there at G101. We've got our command wire sending voltage, seen here in red. And we've got the resulting current flow, the work being performed, in green. And as you can see, this high side driven circuit has current beginning to flow as the command is given to the always grounded VTT oil control valve solenoid. As we establish current flow through an inductor, a magnetic field is going to build. That magnetic field building can be seen right here. If the magnetic field wasn't building, as we established voltage source to that grounded solenoid, current would flow straight in, and the angle of this ramp would tend to go more vertically. However, we're seeing it here coming in at an angle, or what we refer to as a current ramp. Lenz's law basically states as that magnetic field builds, it creates counter voltage or current flow that opposes the current used to establish that ramp. The fact that the magnetic field is being built is fighting the fact that current is flowing, and it's resisting it a lot at the beginning stages of forming this magnetic field. However, as the magnetic field builds over time, the amount of counter voltage or opposed current it creates diminishes, and that allows us to see this ramp increasing in current amplitude over time. In this area here, what can be seen here is a dimple or deviation or bump, if you will. We refer to commonly in the industry as a pintle bump. And the reason this pintle bump occurs is due to Faraday's law. Any change in magnetic field is going to produce a voltage. That's what that law states. Well, that voltage is going to create a counter voltage, a current, if you will, that opposes the current being built, and that's what can be seen here. So what is the change? If we take that ferrous metal of the solenoid and we move it within the field windings, it generates a voltage. That's exactly how a crankshaft position sensor works, for instance. That voltage opposing the current flow is going to create a dimple, a momentary drop in measured current in that circuit, and that's seen right here. What am I getting at? This pintle bump states that the solenoid physically shuttled, meaning when our PCM commanded the circuit on, enough current flow was created in the circuit to generate a strong enough magnetic field to move the solenoid. Stated another way, there's nothing wrong with the circuit and it's functioning just fine. So what am I getting at? Our made-up fault is as follows. The DTC P0011 that we could have potentially had, or were pretending to have, means the variable valve timing system detected a malfunction. The PCM references the crankshaft position sensor for reference, for home base, if you will, and measures the offset of the camshaft position sensor of our intake camshaft, the one that is being phased. That is reported to the PCM. The PCM decides on a phase angle and sends it as a command, a duty cycle command, to the VTC control solenoid valve. That valve located right here is going to direct pressurized oil up through the system to cause that phaser to move. That didn't happen, and we had to understand why. And by using data to watch that occur, we made a decision that there was something wrong with the system. By using bidirectional control system tests, we could manipulate the system as a whole, factoring in not only the mechanical components, the hydraulic circuitry, the electronic control, but the PCM's logic and feedback from the camshaft position sensor to determine the entire system's functionality. Pretending a failure occurred, we would then leverage the power of bidirectional control through the Bosch ADS 625X to manipulate the individual components, in this case, the variable camshaft timing oil control valve solenoid, all while simultaneously monitoring the circuit on a lab scope, the Bosch MTS 5200. And we are able to pinpoint what component, if there was one, that is faulty and why. So as you can see, drivability is much easier with a game plan. And it is getting more difficult over time due to layers of complexity being added almost on a daily basis to the vehicles you and I have to deal with on the day-to-day. So leveraging the power of service information, we can educate ourselves on how the system we are addressing truly functions and the players or components involved. Leveraging the power of our own knowledge acquired over time, we can perform the tests adequately and properly to determine if components are functioning properly. And leveraging the power of a scan tool, we can manipulate these systems easily from the driver's seat before determining where to go under the hood when we decide to roll up our sleeves. What's neat about this Bosch ADS 625X is it incorporates everything all in one unit. Service information, a robust scan tool with great graphable data giving us a sense of direction before we get started testing. Bidirectional control that allows for optimizing system tests to prove out if the system's functioning properly or not. And taking bidirectional control a step further through individual component functionality, we can turn components on and off at will with the push of a button wirelessly from the scan tool while testing the systems hands-on through live circuit activity. Leveraging the power of this Bosch ADS 625X, we use the easy test to drive us towards the more pinpointed, more involved pinpointed tests. And it gave us a reason to test, justification to invest more time in a certain area. That's tremendously powerful as a diagnostician to aid in not only accuracy, but efficiency. And I always say when you have accuracy and efficiency, you have confidence. And that's worth more to me than any amount of money. I'm Brandon Steckler, Tech Editor of Motor Age Magazine, and I thank you for joining me on this episode of Mastering Diagnostics. We'll see you next time. Take care.